Thanks, JC. Okay. All right, so, okay. So as I was saying, I think today is going to be a really fun day. It's going to be a little shorter than usual. There's just one main idea I wanted to get across. And that main idea was this idea of looking at those energies of bonds and atoms and using that to get to human scale material properties. So like, how hard can you pull on steel before it breaks? You know, how like stiff or squishy are materials, and what is the sound speed? We're not going to do sound speed really, but we're going to look at like tensile strength and kind of compressive strength of stuff. And I don't want to spoil what our like big group project is, but it's going to be good. So the agenda is similar to last time. Again, I'm gonna quickly review scales of atoms and densities and energy scales, and then I'll give us a new problem. This is actually the agenda from last time, and then we'll do our group problems and review. So quickly to review, atoms. The size of atoms is angstroms, which is 10 to the minus 10 meters. It's 0.1 nanometers. So size of atoms is going to be important. We're going to be making little boxes, thinking of little volumes, and they're going to, you know, the length we're going to be talking about is angstroms. And actually, for most of the time, we're going to be talking about atoms with at least the third or above shell filled. And so we're just going to use a shorthand for most atoms that their size is actually 3 angstroms. So if you know you're squaring, that's going to get a 9, and so that will give you an extra factor of 10. So you might want to carry that around. So yeah, 3 angstroms is the size of atoms. That's going to be important. Okay, so next thing is the atomic energy scale, that scale of bonds. You know, we think of atoms, materials as being these cubic lattices of atoms. So each atom has, you know, neighbors, up, down, left, right, back, forth from it. And the scale of the energy linking those atoms together is the electron volt scale. What you really want to remember is 10 to the minus 19. It's an energy scale, so it's in joules. So we have, you know, 10 to the minus 10 meters for length scale of atoms, 10 to the minus 19 joules for energy scale of atoms. And we're going to, you know, 3 angstroms, we're going to say 4 eV about for the energy scale of most bonds. So we've got all that ready to go. So now the question, and the question is, what is the tensile strength of steel? So I'm going to explain how to set this up. I'm going to get you guys going, and then I'm going to ask you to do some like second parts of the calculation. But what are we talking about here? What we're talking about is, let's say we have like some cylinder of steel, and we grab onto it and we start pulling on it. And we want to know, and you know, you could have different amounts of steel. You could have like a thin steel wire, you could have a big thick steel like column, and the force needed to break different ones is going to change. As it gets thicker, it's going to be more force. And so what we really care about is what stress on the steel is going to cause it to break. That's kind of this right question for any size thing of steel. It's that force needed divided by the area, or in essence, the pressure that you're applying like on the steel or in some plane of the steel. And so this question we're interested in is like, how much pressure, force per area do we need to apply on the steel to cause it to rip or break? You know, this is important if we're making buildings or, you know, bridges or other stuff. And normally, you know, this is going to be experimentally verified. Very important because we'll note that our order of magnitude isn't going to be quite right for various, you know, dirty real world reasons. But, you know, this gives us a way of at least like tackling the problem and thinking about it. So what we're going to do is we're going to think about, okay, let's zoom in and let's just think about like if we had kind of two atoms together and how hard would we have to pull to like break those two atoms apart from each other. And then we can, all we want is a force per area. So we can have like the area between two atoms. And then if we figure that out in the kind of atomic scale, then we can just shift to our human scale units, and that will kind of give us the right answer at the human scale. And remember, the answer we're looking for is a stress or a pressure. Pressure is going to be in newtons, which is a force per meter squared, or pascals. Yeah, so now I'm going to get to switch to the iPad, and it's going to be great. So, and I can't unless I make the iPad a co-host. So I will do that. Okay. What do you guys see right now? Do you see the iPad? Maybe I have to stop sharing here. There we go. Now you guys can all see the iPad. Okay, cool. So let's see here. We were interested in a force per area. And so we're thinking about two atoms, and there's kind of this connection between them. And we want to estimate how much force per area do we need to do to break the bonds. So what we're going to imagine is we're going to imagine, well, actually, each of these atoms is kind of in a bounding volume. And that bounding volume is going to be 3 angstroms on a side. And we know the energy need, so things we have. We know the energy scale, which is 4 eV. And we know the length scale. So energy scale is 4 eV. Length scale is 10 to the 3 times 10 to the minus 10 meters. So those are our scales. But now we're going to add one extra thing. So we want a force per area, and we have an energy. So we're like, okay, well, how do I get my energy, link up force and energy? And so what we're going to figure out is, all right, what I really need to do is I need to apply the force over some distance. So if I apply a force times a distance, that gives me an energy scale. And so what distance are we going to apply this force over to break the bond? And we're going to say that we need to apply that force over the atomic scale. If we like grab one of these atoms and we pull it an atomic distance away, so we move it from here to there, then we're going to say that breaks the bond. And so we want to find out what force, when we multiply it by the distance of 3 angstroms, will equal this correct energy scale. We're applying enough force to do the work to equal that bond so we can separate them. The bond is pulling back, it's kind of the spring that's pulling back. And so what we find out, we're looking for the force that's equal to this energy over this distance. And so the energy is 4 eV, and the distance is 3 times 10 to the minus 10 meters. For eV, we're going to use our human scale, which is 10 to the minus 19 joules, or newtons times meters. So we get 10 to the minus 19 Newton meters over 3 times 10 to the minus 10 yeah, sorry. So this is kind of the answer for our force. I don't actually want to keep going from here because I was going to let you guys do that. So that's our force. But that's just a force between kind of two atoms. But what's the area between them? Well, the area is going to be that atomic length scale. So really, what we figured out here is the force we want is this energy, the atomic energy scale over the atomic length scale. And we really want a force per area. So we're going to divide by another length scale squared. So we're really interested in estimating this kind of energy per length cubed. And so now what I wanted to ask you guys to do was to take the 4 eV as the energy and this length cubed of a atomic scale and figure out what is the answer in pascals or newtons per meter squared. So I want, what is this number? What is this force per area in newtons per meter squared? Okay, so what were we trying to find? We were trying to find this, this force per area. And we said, okay, that's going to look like actually an energy per volume. And so that's going to be 4 eV over 3 times 10 to the minus 10 cubed. And that's going to be 4 times 10 to the minus 19 joules or Newton meters. This is going to be 3 times 9 times 10 to the minus 30 meters cubed. So 4 and 3 are about the same, and 9 is about 10. So that's 29. So then I think just exactly like Venkat said, this is about, this 29 comes up, so it's 10 to the 29 minus 19 newtons per meter squared, because those meters and meters cubed cancel. So that's 10 to the 10 pascals. So that's 10 times 10 to the 9 or 10 gigapascals. And so that this is interesting. So this seems like high. So Venkat was saying in the chat that this seemed a little high, but actually it's about right. So steel varies between like 500 megapascal and like 2 gigapascal as its ultimate tensile strength. So we're actually in like about the right ballpark. And interestingly, if we did this for most materials, so if we do this for like rock or some other, wood or something else, ceramics, the actual tensile strength we'll find is going to be too high, sometimes by an order of 100 or 1,000, because there's going to be little micro imperfections, there's going to be cracks, there's going to be dislocations that can concentrate stress and make so this is like for a pure perfect material where every atom is bonded and it's like a perfect crystal. But just by doing this, we actually got around the right scale. So that's really cool and exciting. And this shows kind of that this little atomic picture that we have actually works. So that was our first question. Yes, and David White says that graphene has a tensile strength of 1 terapascal. So yeah, and so I guess maybe what's happening there is I'm not exactly sure why it's like, a little even higher than this. Yeah, but you know, in essence, what must be happening is there's more bonds, or the bonds are a little stronger, or and graphene doesn't have any of these dislocations or anything that can make it weaker. So this is kind of the maximal atomic scale of things that can hold together before they break. Okay, so
does it matter that we only looked at one atom?
So
like, shouldn't there be forces between all of the atoms? Like, did we just break one atom with our tensile strength and we bent our steel like a minuscule amount?
Yeah, so remember, what we're really interested in is this force per area. So in essence, we found the force per area needed for like one between two atoms. But now if we want force per area, if we wanted the force necessary, now we can like multiply by the area of like, this whole material. And that will give us a much bigger force. But this is the correct force per area for any size. So we're kind of saying that the same force per area for one atom, if we have two times the area, that would be two atoms. And if we have, Avogadro's number of atoms, then it comes up to, these mega or gigapascal kind of things. But yeah, the force is going to be really small, but the area is also really small. And so it actually like comes out to this, big pressure. Okay, so now I've got another question for you guys. So I'll share my screen again. So now the question is, all right, we learned about how to figure out if I'm like pulling on a material, this kind of pressure scale that's equivalent to the bond energy scale. And if I get above that, if I'm applying more pressure, then the atoms can like hold each other together, then that's what breaking means. So now the question is, how tall can mountains get on Earth? And so the idea here is, well, rocks also are kind of like steel, similar sized atoms and probably similar bonds. And so maybe we can figure out some way of, how much pressure some rock is at the bottom. And if that pressure gets too high, then the rock isn't, those atoms in the rock aren't going to be able to hold together. They're going to break. And so then like, the bottom rock isn't going to be able to hold up the top rock. It's going to flatten and squish out. And so the mountain is only going to be able to get so high. So that's my question for you guys as we split up. I'll split us up into groups. Is how tall can mountains get? So this is